Shiver from Central Washington University, and today we're going to be talking about simple harmonic motion. So first question, what is simple harmonic motion? Basically, an intuitive understanding of it is it's the motion that occurs when an object is accelerated towards an equilibrium point. The size of the acceleration is dependent upon the distance of the object from that midpoint, from that equilibrium point. So let me make some sense out of that for you. How do we use simple harmonic motion? Well, what we do is it can serve to model mathematically a variety of different motions, such as the oscillation of a spring, or perhaps the motion of a simple pendulum, or the vibration of a string. Now, taking a look at it to make some sense out of those definitions, you have a spring here, and in slide number 1, or part 1, it's sitting at its equilibrium point. And if you think about holding a spring, there's some point where it's neither stretched nor compressed. It's just there. That's that equilibrium or that midpoint. If I scrunch the spring up like I'm doing in number 2, if I compress it, I'm shorter than it started out as at its equilibrium point. When I let that spring go, it's going to stretch past that equilibrium point and out a little farther. And then it's going to go back to the equilibrium point, compress, back to the midpoint, stretch, and it's going to repeat this pattern. Now, what we're going to do is we're going to kind of veer off the real world and go into math land. We aren't going to consider friction. We're not going to consider air resistance. So once I let this spring go, it's going to do this forever. Okay? We know that's not true in real life, but that's the behavior we're going to model. All right, there's two things that might be of interest to you, slightly different than what we've done in the past. The period, again, is still the time it takes to complete one full cycle, while the frequency is a number of complete cycles per unit time. What's interesting in these problems is that instead of measuring in radians, we often measure in time, in seconds. So along our x-axis, instead of our pi and 2 pi, we're going to have 1 second, 2 seconds, or 1 minute, 2 minutes. So we're going to be measuring in time. Based on that, we can understand clearly that, let's say that the period of one of these spring oscillations, it takes 4 seconds to complete. Well then, wouldn't the frequency be 1/4? Okay? How much of that cycle was completed in 1 second? Well, 1/4 of the cycle, because it took 4 seconds to complete the entire thing. So frequency is often indicated as 1 over the period. However, we're still going to have to calculate our B value the same way that we've done it in the past. But do know that you can talk about frequency in terms of 1 over period. All right, we're going to take a look at one example. And this is a classic that all pre-cal teachers are pretty familiar with, the Tarzan problem. We've got Tarzan swinging back and forth on his grapevine. As he swings, he goes back and forth across a riverbank, going alternately over land and over water. Jane decides to model his motion mathematically and starts her stopwatch. Let T be the number of seconds the stopwatch reads, and let's let Y be the number of meters Tarzan is from the riverbank, with Y being positive when he's over the water and negative when he's over land. Assume that Y varies sinusoidally with T. At T equal 2, Jane finds that Tarzan is at one end of his swing, 23 feet over land. She finds that when T is 5, he reaches the other end of the swing, 17 feet over water. All right, so here's a diagram of what Tarzan is doing. And from what we just read, let's get 2 points that we know are occurring. At T equals 2, Tarzan is 23 feet over land. Remember, we decided that over land would be negative, so he's at negative 23 feet. That would be the minimum. He's reached the farthest back that he possibly can. At t = 5, he's reached the farthest out over the water that he can at 17. So one end of his swing is here at -23 feet. The other one is at 17. All right, so let's go ahead and start by graphing this, and then we'll try to write a function for it. Okay, I've already marked on my axes the maximum and the minimum point. So what can I do? Well, from that max and min, I can find my amplitude. All right, my maximum point was 17. My minimum was at -23. So again, add those two and divide by 2. So my amplitude is 20. All right, next what I want to figure out is where is that horizontal line? Has it been shifted up or down? So I'm going to try to figure out my horizontal translation. The way I can do that is I can either add 20 to my minimum or subtract it from my maximum. So if I add 20 to my minimum, it looks like my horizontal occurs at y = -3. So -23 plus 20. So I'm going to go ahead and draw that in here. All right, so that means that my shift was down 3. My axis moved from 0 down to -3. So my D value is -3. Okay, so I found A and I found D. Now I need to figure out B and C. So let's start by finding the period. Okay, well, to find the period, maybe I want to go ahead and graph it first. I know that if this is the minimum and this is the maximum, halfway in between here, I must have crossed my axis. Okay, in this case, y = -3. So between 2 and 5 seconds must be the point where I cross. So I need to find halfway between 2 and 5. So 2 plus 5, I need halfway. So it occurs at 7/2 or 3.5 seconds. So at 3.5 seconds, I'm going to cross the axis. All right, well, same thing here. It must have occurred, how far is that from 2? That's 1.5 seconds after 2. So 1.5 seconds before 2, or at half a second, I must have hit that axis again. And again, after 5, 1.5 seconds after 5 would be 6.5. So now I can quickly sketch my graph, get an idea of what it looks like. All right, so let's go ahead and determine the period then. So now that I know what it looks like I have gone from 1/2, all the way through 6.5 before it repeats. So from 6.5 to, from 1/2, to 6.5 is 6 seconds. All right, so my period is 6 seconds. Now frequency for these problems is often given in time, rather than radians. So my frequency can be defined as 1 over the period, or 1/6 of a second, or 1/6 of a cycle, 1/6 of a cycle occurs every second. All right. However, to find B, we need to go back to what we've done in the past, using period is equal to 2 pi over B. So my period is 6, 2 pi over B. So 6B equals 2 pi. B is 2 pi over 6, or pi over 3. So there's my b value, pi over 3. The last thing to do, of course, is to find that phase shift, which again is the toughest. All right, for my phase shift, what I want to do is I want to figure out in a cycle of 6 seconds, where does the maximum normally occur? Well, it's always 1/4 of the way through, so I'm going to take 1/4 times my 6 seconds. Okay, that's going to give me 3/2, or at 1.5 seconds is normally where my maximum occurs. All right, my maximum occurs not at 1.5, but at 5. So to figure out my phase shift, I'm going to take the 5 where it is occurring minus the 3/2, okay, which gives me 3.5. So my shift has been 3.5 seconds to the right. All right, so now we just put all our pieces together and write our function. So we'll call this T of x for Tarzan. T of x is equal to our amplitude, 20, times the sine. And it might be more convenient here, even though I didn't do it, you could have written this as a cosine function. Your choice. 20 sine pi over 3, and remember, again, we've got to leave our pi over 3 on the outside to get that phase shift, x minus 3.5, and then minus 3 since we shifted down. So nothing new today. Same procedures that you used yesterday for writing your functions, just a little bit different behavior. Instead of thinking about an angle circling around this unit circle or around a circle, we're now thinking in terms of something that's bouncing up and down or swinging back and forth. So simple harmonic motion behaves very similarly, just a slight difference. See you again in a little while.